Okay guys, we're going to do something new that we've not done in Biology 1, so it's brand new to Biology 2, which is just, um, we're going a little bit more in depth into certain topics that we've done. So this is genetics and statistics, so a tale of two hypotheses. So that's what we're going to look at here. So consider the story. We have two tigers at a zoo, and they're bred together, and they have 4 cubs. All right, I can just picture the Punnett square in my head right now with the 4 slots. So that's what we're going to do. So 2 of the 4 cubs are albino tigers. Based on that, Kristen hypothesizes that both of the parents must be carrying a recessive gene for albinism. The cross would look like this, right? That would make sense, right? That's how, I mean, you have 2 parent tigers that are normal, so they have to have a capital A. So they have to be carriers, right, for both of those cubs to get that. So if Kristen's hypothesis is accurate, the Punnett square would look like, oh, let me go back, shoot. Okay, so it would look like this, and we're going to fill it out. So if you had 2 parents that were heterozygous, both of them, you have this. So you have 2 capital A's, which would be an orange tiger, capital lowercase, which would be an orange tiger, another capital lowercase, which would be an orange tiger, and then finally we get these 2 lowercase, which would give you the albino tiger. Now this is all just like a hypothesis, right? We don't know. We've not gotten the genetics from these tigers, but we did see what their children were, the cubs, to help us figure out what mom and dad have. Okay, so once we do that, we're assuming that there is a 1 in 4 chance, a 1/4 or a 25% chance that you're going to get an albino tiger. All right, so the fact that you got 2 of the 4 to be albino is pretty, that's pretty good odds. If you're wanting the white tiger, it's pretty good. Good for you. So let's get rid of this. Go to the next slide. Your friend Emily is unconvinced. If your hypothesis is correct, then only 1 of the 4 kittens should be an albino. And that's the person saying that they're dumb because they think that it's the big A, little a, big A, little a. All right, so, but isn't 1/4 pretty close to 2/4? Is 1/4 close to a half? Maybe the difference is just due to chance, which we know that there's chance. Punnett squares are not set in stone. Once I flipped a coin 4 times, I got heads 3 times. Sometimes it just happens that way. Maybe you just got lucky and got an extra white kitten. Here's the problem. With coin flips, you don't get genetic mutations. So that's what we're looking at. Was there a mutation involved here? Did these parents, did they possibly both carry this gene, or was there some freak mutation that happened? So that's what we're going to look at statistics to try to figure that out. Was it some mutation, or could this really have happened? So the only way to solve this is to do a statistical analysis. They call those everyone will say chi-squares. The purpose is to determine whether the results are statistically significant. It's not just, oh, we think. This is to try to help prove what we think. So what are the odds that your tigers are both heterozygous for albinism? Or could there be other factors like a mutation? So that's what we're going to look at here. So we get some math, which kind of throws kids off sometimes. So bear with me, and if you're struggling at all with this, let me know. So here's how to do this. You're going to get your observed minus your expected. So like, for instance, on the tigers, our observed were 2 were white. The expected was 1. And you're going to divide it by the expected, 1. And this is summed for all classes. So what that means is that you're summing this for each different type of allele. So we had the white allele, which I just did up here, but we also had an orange allele. So the orange, and this is summed, so you would add them together. The orange allele would be your observed was 2, the expected is 3. So that's how you would fill that in. Okay, so let's go to the next slide, which is going to actually fill that in for us. All right, so to apply the formula, plug in your observed and expected numbers. This will give you, oh, that's not what I meant to do. I'm sorry, guys. Let me go back. Well, if it'll let me go back, there we go. Okay, so this will give you your x squared. So what we have is we did, and it doesn't matter if you do the orange first or the white first, doesn't matter. We know that this is what I just did a second ago. Our orange, the observed was 2. There were 2 out of the 4 cubs that were orange. The expected number, though, would have been 3 when we did that Punnett square. And divide by the expected, which is 3, plus, now we're going to do it for the white. The observed were 2 of the 4 cubs were white. We expect 1, so that's where the 1s are there. When you do this, 2 minus 3 squared divided by 3 is going to be 1/3, right? 2 minus 3 is 1, 1 squared is 1, 1/3. 2 minus 1 is 1 squared. 1 squared divided by 1 is, it's 1 over 1. All right? Now, when you take 1/3 plus 1 over 1, you get 1.33, right? It's basically 1 plus 0.33. So you're 1.33. Now, the question is, okay, well, what does that mean? What does 1.33 actually mean to us, and what does that tell us? Well, we use this chart to help us with this. Now, degrees of freedom, you're always going to use 1 less than the original number of classes. Now, remember, classes were how many alleles were there? Where we had white and orange. We had 2 classes. That's it. We are going to use 1 less. So in this case with the tiger cubs, this was how many classes we had. We're going to use 1 less. So we're going to look at that row right there. So what we're looking at is 1.33, and I know I'm jumping ahead of myself a little bit here. I'm going to go to the next slide, which would be somewhere in this vicinity. So let me go ahead and click to the next one. Get that off there. All right, so it's between 20 and 30% columns. So basically this means, what this 20 to 30% means is that this can be expected. If this were true, if it were capital A, lowercase a, the fact that you got 2 white cubs and 2 orange cubs, this could happen about somewhere in between 20 to 30% of the time. Anything lower than 5% shows the differences are probably due to something other than chance, like a mutation. So if we were in this area, we would be like, oh, Kristen was wrong. That wasn't correct. They're not heterozygous. But since it's out here, and of course the closer to 90% you get, the better, we're like, yeah, that can happen. About 20% of the time, that's going to happen with parents that are heterozygous for both traits. Of course, it says results are always better with a larger sampler size. I have been telling you guys that since Biology 1 freshman year. The more trials you can do, the more samples you can do, the better. Of course, that's a little hard when you're talking about mating tigers. So, something I meant to do. If you find that you have a poor fit, then you should just reject your hypothesis. So if we would have been in 5% or lower, I would have been like, our hypothesis was wrong. Something else is at play here. Maybe there was some mutation in one of these tigers. Something like that. Or it could just be, yeah, if it's due to chance. Okay. I didn't mean to go backwards. I'm struggling here with this today. Okay, here we go. So Emily thinks she gets it now. So she looks at another case. She breeds 2 black mice together, and she finds that over the course of 3 years, the parents produced 230 brown mice and 710 black mice. She hypothesized that the parents must be heterozygous then. So we're going to go through all of this again. So if they're heterozygous, I'm going to do a little Punnett square here. It's going to be just like the tigers though. All right, I'm assuming that black is the dominant trait since there's 710 of them are black and 230 are brown. So let's look at this. My observed is going to be, and it's sum for all classes, so I'm gonna put this down here. So let's do the brown mice first. My observed is 230. Let's see here. How am I getting the 2? Oh, produces 230, okay. I have a different number on mine. That's why I've got 330 and 810 on my paper. Okay, well, I'm going to change these numbers because my math is going to be all wrong, so I'm sorry. I'm so sorry, guys. But I had 330 down and I had 810 down. So we're going to go with that, all right? As soon as I started writing it down, I was like, that doesn't look right. Okay, so so my observed is 330, and I'm going to subtract expected. Now my expected, though, I can't be like, oh, 330 minus 1. I can't do that. So I'm going to take 1,000. The total number of mice here are 1,140. So I'm going to write this here, 1,140. That's the total. And I'm expecting a fourth of them, or 25%, so I could say times 0.25. I expect 0.25% of them to be brown. So when I take that 1,140 times 0.25, I get 285. So this is where it is a little bit different with the tigers. The tigers, there were only 4, so I could use those small numbers. This right here makes this a little bit different. This is how I'm going to get my expected. I'm going to add, I'm going to do it for the black mice. 810 is my observed. My expected, once again, I'm going to take 1,140 times 0.75. I expect 75% of them to be that. So that is 855 squared. All right, so we don't get a negative number. And I'm going to divide by 855. All right, now what this gives me, I don't know if you can see under here or not. This is going to be 7.1. I hope you guys can see that okay. Plus, this one is going to be 2.368. So when I add these together, that is going to give me 9.468. All right, now then let's look up here. We have 2 degrees of freedom, right? Or not 2 degrees, we have 2 classes. So we are going to look at one less. So we're going to look up here for 9.46 is way down here. All right, so that is a poor fit. So I would say that's not a good hypothesis. That something else was at play here. Maybe it was genetics, and with mice and in fur color that can happen. Here's a chart though. If this makes it a little bit easier for you, I just filled in that down there. But the observed 330, 810. Remember my expected. I took 1,140. That was the total, and I multiplied it by either 75% or 25, so by 0.25 or 0.75, and that's how I got the 2. Oh gosh, I've got this backwards. I did my brown mice first. But sometimes doing a chart like this can help you out. All right, so it gives you the total observed, which was 1,140. The expected should also be 1,140. Those should add up. Your observed and your expected. All right, so anyways, that is just an example of one. There is a calculator on, you can find them, you can just Google search them and find them, but there are calculators where you can do this. But I do want you guys to know how to do it. Even people that this is what they do for a job, they still need to know how to do that. All right, so anyways, that's an example of chi-square and how you complete this. We are going to be doing a kind of a corn lab with this, so you're going to need to know how to do those numbers. Now with you guys, I believe, is that the end of your notes? Let me check the end of your notes here. I thought, no, it's just that problem we just did. All right, so anyways, that would be it. Tomorrow we'll start that corn lab. If you need any help at all, let me know, and I will get back to you. Have a great rest of your day. Bye.